Good afternoon, AP Stats kids. It's Monday, April 20th. I hope everyone's safe and healthy at home. Thanks for stopping in again this afternoon. Happy Patriots Day. I know that may not mean mean anything to most of you, but I grew up in the Boston area, and I now live in Maine. You hear the Boston accent, and Patriots Day is a holiday in those two states. I don't think it's a holiday anywhere else, but it's a big day in New England, kind of a fun day. Most years they run the Boston Marathon. This year, of course, they're not running the marathon. So anyway, happy Patriots Day from New England. And if any of you end up going to school in the Boston area, you'll see next year it'll be a super fun day, and they run the marathon, and everyone has a day off. So anyways, welcome back. So today, tomorrow, and Wednesday, Luke and I are going to do probability. That's one of the big, what I call one of the four themes or threads of the course. You know, most typical years it would be 10 to 20% of an AP exam. I don't even want to speculate on this year's test because it is different. But you know, somewhere in one of those two free responses, you know, I'm going to stick my neck out and say you'll get some probability. So Luke and I wanted to spend 3 days on it. So today I'm doing conditional probability, two-way table, maybe basic probability. He's going to do binomial and geometric probability tomorrow, and then Wednesday I'll be back to do random variables. So we want to do a good job with probability. It tends to be perhaps a more difficult theme or thread for students. So we decided we wanted to do a pretty good job with it. So anyway, there's our intro slide as always. Again, I'm Brendan Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. It's our school vacation week this week. Luke is from East Kentwood High School in Michigan, and hopefully you've seen both of us. So I think this was your homework problem from Friday, and Luke did some free response questions. So the seniors at 3 high schools were surveyed about their plans after graduation. The table shows the responses classified by high school. So I like to call this a two-way table. And many times we're trying to see, is there some relationship between your high school and maybe your plans after graduation or something like that. These totals over here on the right and down the bottom, it feels like sometimes we give you those totals and sometimes we just give you the table without the totals. If we give you a table without the totals, I think it would probably make sense to just have all of those different totals. It won't take that long, especially with a calculator. And almost always I need at least some of those totals. So one senior from the high schools will be selected at random. What is the probability that the senior selected will not be from high school B, given that the senior responded with a choice other than college? So that last sentence, you know, that you might need to read that twice. There's kind of a lot going on that last sentence. So I'm going to read that last sentence again. What is the probability that the senior selected will not? So that's nice. I mean, that was underlined for us. If not, I probably would have circled it. Be from high school B. So I'm going to focus kind of on high school B over here. Given that, so that's kind of the key words, that this is what we call a conditional probability. And I'm going to do some more with that today. So what we call conditional probability. There's a constraint, there's a condition, there's a limiting factor on how I calculate my probability. Given that the senior responded with a choice other than college. So I guess I'm not going to worry about this column here. It said other than college. So I just said, well, we're not going to worry about those 418 students who went to college. So it felt like my denominator wanted to be all of those students who either chose work, chose military, or chose undecided. So down here, that was my denominator, and I added those up and I got 538. And I actually could have gotten the correct answer based upon that, but you know, let's keep going and really understand the problem. So going back to this sentence, what is the probability the senior selected will not be from high school B? So I guess I'm not going to worry about those students. I guess I'm not going to worry about those students. I guess I'm not going to be worried about those students. So I guess I'm not worrying about college, right? and will not be from high school B. So I actually had almost two things here that I didn't really need to take into consideration. This felt like a harder one to me. So some of them, I think I'm going to do a couple of multiple choice and then a free response or two. This one was a little bit harder for me. So it looks like I need those 99 students and those 83, and I need those 49 and those 31. I need those 63 and 71. And if I did my math correct, I get 396 over 538. So two-way table. Again, these totals were given to us. If they weren't given to us, I think it's well worth your time to add those in typically. And then really make sure that you understand the questions. Sometimes the wording, it feels like students kind of reverse what we're asking them, and that can be easier to do than you think. So really spend time just understanding the question and making sure you're addressing that question. So that was the homework for Friday night, I guess. Again, here's a couple of websites. I think I've gone through these, so I'll just go through these really quick. But any questions about this year's exam, please, all this information is here. The College Board's done a wonderful job of trying to get that information out to everyone. So I'm going to try and address the two concepts of mutually exclusive and independence today. They're two completely different concepts. My students will struggle with these, and it feels like in most books they're sort of introduced maybe in the same section in your textbook or right next to each other, and they can be a little bit confusing. So I'm going to try and tackle both those today. Two events are mutually exclusive or disjoint. Those two terms mean the same thing, and I think I've seen both of those on previous AP Stats exams, so feel comfortable with both terms. So two events are mutually exclusive or disjoint if they cannot occur at the same time. So the probability of A and B equals 0. So you cannot be in the state of Massachusetts and the state of Maine at the same time. You can't do it. You're either in Maine or you're in Massachusetts, or you're in neither, but you can't be in both states at the same time. Mutually exclusive events are not independent of each other, and I capitalize that not for a reason. That's harder for kids, I think, and my kids sometimes will struggle with that concept. Okay, sorry about that. So mutually exclusive events are not independent of each other. And that may be not what your brain is telling you. So here's a Venn diagram. And I say to my students, let's assume that the only two grades you could get in my class are A and B. And they love that. They say, yes, Mr. Murphy, we love that. That's great. So let's say you can either get just an A or a B. There's no other options. So there's no overlap, unlike that Venn diagram where it looks like, you could be in both A and B. So you either get an A or you get a B, okay? So those two events are clearly mutually exclusive or disjoint. There's no overlap. As I say to students, at the end of the 45-day quarter 3 or quarter 4, whatever, there's a whole bunch of grades in the grade book. I will do a little math, and but the numbers are there, and your grades are already predetermined. I just maybe need to worry about some percentages or add in some final homeworks or something. So let's say you get a 96 at the end of quarter 3. Well, that's an A in my school, probably an A in all of your schools. Well, those numbers, again, are really predetermined. I'm not really doing anything other than going to my computer and maybe finishing up a few little odds and ends. Well, if you get a 96, that's an A. Well, the probability of you getting a B is going to be 0. You're not going to get a B. You're going to get an A. So those events are mutually exclusive. There's no overlap, but they are not independent of each other. Independent events, the probability of the second event isn't impacted by the probability of the first event or something like that. So your eyes are telling you that they're independent. They're not hitting each other. There's no overlap, but there's no overlap. But that's really not what independence means. So I have my little coin here and my Six-sided number cube, if you ever hear that term, six-sided number cube, I guess some of us might call that a dice or a die. I think those two events are independent of each other. If I were to, shake them in my hands and roll them or throw them, the outcome of this coin is clearly not impacted by the dice or die or vice versa. So most students say, yeah, that's pretty obvious that those are independent events. The probability of one isn't impacted by what happens with the first event. So I have problems to deal with both mutually exclusive and that independence, and hopefully I can get to all of them. So here's a multiple choice question from the 2007 exam. A fair coin is to be flipped 5 times. And so again, a fair coin just means that the probability of heads is equal to the probability of tails. You don't get one more than the other. So that's all a fair coin means. The first 4 flips land heads up. So I guess I get heads, 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 and heads. What is the probability of heads on the next 5th flip of this coin? So I usually just put a little dash there. That would be my 5th flip. And the probability of getting heads here is 1/2, 50-50, however you want to phrase it. Only because each one of those flips is independent of each other. So the 5th flip here is not impacted by what's happening to any of those first 4. So the answer is B here. Relatively straightforward. 76% of the students in 2007 got that problem correct. And if we start to look at some of our distractor answers, well, probability of 1 means it has to happen. So that doesn't make sense. I don't have to get a heads even if the first 4. E0, well, that means I can't get a heads. Well, I guess I could flip a coin 20 times and get 20 heads in a row. I don't really know. I think C, that sort of looks like the binomial formula. I think Luke will tackle that tomorrow. And D here, I guess, is trying to mimic maybe what I did here. I have heads, 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 and the probability of each one's 1/2. And this, I'm going to raise that to the 4th power, and to get my 5th head. I think that's the probability of getting 5 heads in a row. So that was a relatively easier one. Let's keep going, and they will get a little bit, I think, more difficult here. So this is from 2007 exam. An experiment, so I think I'll underline that word, has 3 mutually exclusive outcomes, A, B, and C. Okay, mutually exclusive, there's no overlap between those 3 different outcomes, A, B, and C. The probability of A is 0.12. The probability of B is 0.61, and the probability of C is 0.27. Which of the following must be true? That's strong language. I think I'm going to underline that, must be true. So you can see down here, I've drawn my Venn diagram, and clearly my circles, they're not proportional to the probabilities. It doesn't matter. This is just a working diagram for me to sort of solve the problem. So here's outcome A, here's outcome B, here's outcome C, and there's the associated probabilities. Just for the heck of it, I added those up, and I did get 1. So those are the only 3 outcomes that I could get. If it wasn't 1, I might have put a little number kind of out here, the rest of the Venn diagram, but it's 1, and so I have my 3 circles, and I think I'm good. Well, Roman numeral 1 says A and C are independent. Well, we just talked about mutually exclusive events are not independent of each other. So let me go back to that slide. Mutually exclusive events are not independent of each other. It's an important concept, and there's 2 different major concepts going on here. So make sure you're comfortable with that. And I think in some ways that's really what this problem is testing. Do students understand that mutually exclusive events are independent, are not independent of each other? Excuse me. Mutually exclusive events are not independent of each other. So A and C are independent. Well, that's false. That's false. Because of that, I can actually circle the answer D here, because all the rest of them have a Roman numeral 1. And so literally, if students could understand that mutually exclusive events are not independent of each other, this problem wasn't all that hard. But let's keep going and see if Roman numeral 2 and 3 make sense. Well, the probability of getting A and B is 0. Yeah, that makes sense. You're either in A or B. There's no overlap. You have to be in A or B. So you can't be in both at the same time. So the probability of A and B is 0. That makes sense. The probability of B or C is the probability of B plus the probability of C. Again, that's a true statement only when there's no overlap. If there was an overlap, we'd have to worry about subtracting the overlap, but there isn't. And so I had Roman numeral 1 is false, Roman numeral 2 is true, Roman numeral 3 is true. So I got D. Now you can see that 35% of the students got that right. That's a lower scoring multiple choice. And again, I think it's this sort of confusion about mutually exclusive events and independence. So hopefully you're feeling a little bit better about that. Mutually exclusive events are not independent of each other. That slide was there for a reason, and hopefully that makes a little bit more sense. And I think we got some free response coming, so I'm going to try and tackle that as well. So one more free multiple choice, and then we'll dive into some free responses from 2012 exam. So a complex electronic device contains 3 components, A, B, and C. So I'm making some sort of device, and there's 3 different things that go into it. The probability of failure for each component in any one year, 0.01, 0.03, and 0.04 respectively. I guess if I owned the company that was making this complex electronic device, it would be great if that was 0, 0, and 0, meaning every single part was perfect. That's not the world we live in, unfortunately. So you know, we're going to get some parts that aren't perfect, unfortunately. If any one component fails, the device will fail. Well, that makes sense. If either A, B, or C doesn't work, it makes sense to me that the complex electronic device is not going to work either. So that makes sense. If the components fail independently of each other, so the outcome of A is impacted by B, or B isn't impacted by A, vice versa for all 3. So that's super important. Like, that's super important to solve this problem. What is the probability that the device will not fail? Again, the College Board seems to be underlining not fail or not pass or whatever. So that helps. That's important. We're not trying to confuse or trick kids here. What is the probability that the device will not fail in 1 year? So I said the probability of A failing is 0.01. So the probability of A succeeding or success, I guess, is 0.99. It either fails or doesn't fail. Probability of B failing is 0.03. So the probability of B success is 0.97. Probability of C failing is 0.04. The probability of C succeeding is 0.96. So I think those are the 3 numbers that I need. I could see very easily students maybe multiplying those 3 numbers here and getting one of the distractor answers, or adding them or something like that. But those are the 3 numbers that I need. Success, success, success. Not fail means success. So I said PA success times PB success times PC success, and I got 0.921808 or something like that, those 3 numbers. I'll go to the calculator real quick just to check myself. And I'm hoping that that's a relatively high number, i.e. close to 1. I want to make all of my different machines, whatever a complex electronic device is. And I would love it if every single one of them was perfect. That would be dynamite. That's unfortunately not the world we live in. But I still want this number to be relatively high, and I can live with that. 0.92, 92% of the time, or over the long term, 92 out of 100, 920 out of 1,000. Probability only works in the long term, of course. Again, I would like that number to be 1 exactly, but we know in the real world that nothing's perfect. And in manufacturing, we know that we're going to get X amount of whatever that aren't 100% perfect, and we just sort of have to unfortunately live with that. I wish every single problem I ever did every single day in the classroom was perfect, or my students understood it perfectly. And unfortunately, I don't know if I'm that good of a teacher. So well, that doesn't happen every day in my classroom, unfortunately. So okay, so let's see if we can tackle a free response here. This is from the 2002 Form B. We used to call that the international exam. We used to release 2 exams. I wouldn't worry about it, but that's what Form B means. This is free response number 2. So airlines routinely overbook flights because they expect a certain number of no-shows. So I haven't flown in a long time and may not fly for a couple months, but I fly a reasonable amount, and many times the airlines oversell and they ask for volunteers, and my wife and I have taken advantage of that. Many times we've gotten X amount of dollars from the airline by voluntarily giving up our seat. And if you're ever in that opportunity, sometimes it's a great deal. So an airline runs a 5 p.m. commuter flight from Washington, D.C. to New York on a plane that holds 38 passengers. Okay, what we would call a regional jet. I live in Bangor, Maine, and every plane that comes in and out of Bangor is a regional jet, smaller planes. Past experience has shown that if 41 tickets are sold for the flight, so again, there's only 38 seats on the plane, the airline wants to or does sell 41 tickets. And they do that because they know some of the businessmen or whatever just are going to miss the flight because of traffic, or their meeting went longer, or whatever. They decide to stay another day in the city or something. Then the probability distribution for the number who actually show up for the flight is as shown in the table below. So again, if the probability of 36 people showing up is, I guess, 0.46, and 37 people 0.30, et cetera, et cetera, et cetera. Again, I think I would add up those 6 probabilities, and I want to get 1. If I got 0.999 something, I'm not sure I would be overly upset about it, but I want that number to be 1 in a perfect world. Assume that 41 tickets are sold for each flight. So every flight, every day, 38 seats, the airline sells 41. Okay. I think I understand the problem. And again, I think I've said many times that it's well worth spending another 20 seconds, 30 seconds, whatever, really understanding the problem but before you actually sort of dive into the problem. So you can see it's my little sigma there. I did add up and I got 1, so I felt pretty good about that. So assume 41 tickets are sold for each flight. Okay. There are 38 passenger seats on the flight. What is the probability that all passengers who show up for this flight will get a seat? Okay. Well, if 36 people show up and that's it, all 36 people are going to get a seat on the plane. If 37 people show up, all of them can get a seat on the plane because there's 38 seats. And if 38 people show up, they're all going to get a seat again because there's 38 seats on the flight. So I think I just added those 3 probabilities and got 0.92. But I almost walked away from it, and then I said, no, Mr. Murphy, you really need to sort of, put a sentence there or something like that. Make sure it's in context. So many times I just kind of repeat the question asked. The probability that all passengers who show up for this flight and will get a seat is equal to 0.92. So in some of these probability problems, it's easy enough to just kind of look at the table sometimes and get the correct numerical answer. But again, super important. We want some context there. We want to relate it to this problem. What is the expected number of no-shows for this flight? So I've done this problem many times, and I'm not going to say what I'm going to do is incorrect, but what I did didn't exactly address the question. I think a little bit and I could get there relatively quickly. So I said the expected value X is the outcome times the probability plus the outcome times the probability plus the outcome times the probability. So I felt comfortable with that. And you can see here's all my math. So I said 36 people showing up times 0.46 plus 37 people times 0.30, et cetera, et cetera. And I got 36.9. That didn't feel good to me. And I said to myself, wait a minute. On a 38 passenger plane, the expected number of no-shows is 36.9. It took me, a couple seconds. I calculated the number of people who theoretically will show up. So I didn't actually address what they wanted. So 41 minus 36.9. 4.1 is the expected number of no-shows. So my math is correct here. I guess maybe I was just answering the wrong question. I'll show you how to do it sort of correctly down below. I don't want to round that number. Many times on the AP exams when we're grading these, we'll see students, come up with the correct math, 4.1, and then over here they say, 4 is the number of no-shows, because they say things like, well, you can't have 0.1 of a person. Well, this is an expected value, an average, and we don't want to round those. We don't want to round expected values or averages. The average American family has 2.2 kids or something like that. We don't want to round that to 2. So be careful and make sure that you understand that. Don't round an expected value unless specifically told otherwise. So again, in the full sentence, the expected number of no-shows for this flight is 4.1. So what I did wasn't wrong. I guess I was just answering the wrong question, and I had to do a little bit more math to get the right answer. I guess I could have done 41 minus 36, 5 times 0.46. 41 minus 37, or 4 times 0.30. 41 minus 38, et cetera, et cetera, et cetera, and gotten that number 4.1 directly. Same answer. I felt confident that I had done something correct up here, but I just really wasn't answering the question that they asked. So just be careful about that, and again, show your math and notice that I tried to answer the question with a full sentence. So given that not all passenger seats are filled on a flight, boy, that sort of feels like a conditional probability, right? Those two words, given that's the tell, that's the red flag. Given that not all passenger seats are filled on a flight, what is the probability that only 36 passengers showed up for this flight? So I'm just going to go up to my table here and say, well, given that not all passenger seats are filled, I'm not going to worry about the rest of the table here, because 38, all seats would be filled. 39, all seats would be filled. So for the last half of the problem, many times I just cover that up. Just cover that up. 36, not all seats are filled. 37. So I think I just added the 0.46 and 0.30 right down here. What is the probability that only 36 people show up? There's my 36. So that's my 0.46 down here. Sorry about this, hard to just get the whole problem in. In here, I tried to write out sort of in words, maybe the formula that I'm using. And again, I just don't want to show these numbers here. That wouldn't be a very good answer, or just that wouldn't be a very good answer at all. The reader's going to say, where did you get that number? We want to see your backup. We want to see your math. So here, as opposed to saying words, I tried to say it in maybe symbols. What's the probability that x equals 36, given that, that's what this vertical lines mean, given that not all seats are filled, 0.46 over 0.46, 0.30. That's an acceptable answer right there. That's an acceptable, that's an acceptable. All of these are perfectly fine. So 0.605. So that's a nice little problem. Very real world. Every flight I get on leaving Bangor, Maine seems to be one of these regional jets. And my wife and I have been lucky enough at times to take advantage of an old oversold flight and get some money from the airlines, I guess. So let's go look at another free response question. This is from the 2003 Form B exam. Again, two-way table. Looks like I'm trying to see, is there some relationship between age and income? I have my thoughts about that, but perhaps there is, perhaps there isn't. Again, these totals are given to us, marginal totals. If those weren't given to us, I think the first thing I would do is pull out my calculator and add those up. So a simple random sample, that's good. I like the randomness, of adults living in a suburb of a large city was selected. Okay, so I'm taking perhaps a small sample of a large city. The age and annual income of each adult in the sample were recorded. It's all these numbers down here. The resulting data are summarized in the table below. So two-way table, and very typical question. And we're going to ask, a couple, 2 or 3 questions based upon that table and those different numbers. Okay, so same problem. Part A, what is the probability that a person chosen at random from this sample will be in the 31 to 45 age category? So 31 to 45 age category, 89 over 207. That's relatively easy for me to do. And for most of my students, actually, it can be relatively easy for them to do as well. And unfortunately, sometimes we see, an answer like this on the AP exam, and that's all the work that students give us. And traditionally, that has not gotten full credit. Later on, I think next week, I think Luke did some of that on Friday, and I'm going to spend a day on it. Actually, how do we grade the AP exams, and what are we looking for? We call that a bald answer. We want to see some work. We want to see a sentence. We want to see some communication. And sometimes my students fight me a little bit on this, and they say, "Come on, Mr. Murphy, it's really easy. I can read this number from the table, and I can read that number from the table, and I think that's the right answer. Why can't I get full credit?" And again, we want to see your work, and we want to see that you've communicated this well. So I tried to write out in a sentence the probability that a person chosen at random from those in this sample will be in the 31 to 45 age category is 89 divided by 207 equals 0.43. In many ways, clearly the same number, right? That hasn't changed. But I've related it to this problem, and I guess I don't know if I've shown any more work, but I've clearly communicated my answer better. Feeling that maybe I still needed to show a little bit more work, I did, what's the probability that you're in the 31 to 45 age group? 89 over 207. I keep getting that number, and I'm pretty sure that's the correct number. But we don't like these bald answers. This 89 over 207, I'm going to strongly recommend that you don't do that. I think you run the risk of not getting full credit on that problem. Even though it's relatively easy, relatively fast to read those numbers direct from the table, I like to try and teach my kids, just follow it up with a sentence, or give us some supporting work, give us some numbers, give us something. Okay, part B. What is the probability that a person chosen at random, so that random is good, from those in this sample whose incomes are over 50,000 will be in the 31 to 45 age category? Show your work. Okay, well, there it's crystal clear. We wanted you to show work, and so you're not gonna get full credit there if you don't show your work. I like to say to my students, even if we don't say show your work, please show all of your work. I think that really makes sense to do. And sometimes if you make a little math mistake, sometimes we call it a typo. If a reader can look at your math, there's times where you might get partial credit, or sometimes even full credit. So we don't want to penalize for small typos. But if there's no work there, then we can't see what you did. So down here, I tried to write it maybe more formula based. What is the probability that you're in the 31 to 45 age group, given that your income is over 50,000? Well, what sometimes confuses my kids is the way I wrote that feels like it's sort of opposite of the way that the question was asked. They said, "But Mr. Murphy, the $50,000 was first, so they want to do, what's the probability that you make over 50,000, given that you're in the 31 to 45 age group," or something like that. So sometimes students reverse the order, and it's not the order that we presented the information. You're really going to read the language there. Whose incomes are over 50,000. So that feels like that's my condition, over 50,000. right? I think I only want to look at those folks over 50,000. You will be in the 31 to 45 age category. So conditional probability, there's sort of my formula, 35 over 96.364. Again, please show us some work, whether it's in words or math symbols or something. We really don't like, and we don't typically give full credit for what we call bald answers. Based upon your answers to part A and B, is annual income independent of age category for those in this sample? Explain. So let me do another example before I tackle that. So I want to flip a coin. Here's my coin and my die, right? I think I showed you these earlier, right? I either get heads or tails. And I want to roll a six-sided number cube. Again, if you see a six-sided number cube, other people call it a die or a dice. They mean the same thing. I can either get a 1, 2, 3, 4, 5, 6. So my students are 100% convinced that these two events are independent of each other. The probability of the second event isn't impacted at all by the first event and vice versa. So they're pretty convinced that those are independent of each other. So there's two options or two outcomes when I flip my coin. I either get heads or tails. There's 6 outcomes when I roll my six-sided number cube or die. So there's a total of 12 different outcomes when I flip my coin and roll that die. So I drew a little diagram down here. Sometimes I call this a probability tree diagram. I can get a heads and a 1, a heads and a 2, a heads and a 3, heads and a 4, et cetera, et cetera. I can get a tails of 1, tails of 2, tails 3. Those are my 12 outcomes. If I were to list out my 12 outcomes, I would call that my sample space. Heads 1, heads 2, heads 3, et cetera, et cetera, et cetera. So what is the probability that I get a heads given that I got a 6? Well, there's 1 6 here, and there's 1 6 here, and so I can get a heads and a 6, or a tails and a 6. So what is the probability I get a heads, given that I got a 6? Well, I got a 6, I got a 6. What's the probability I get heads? It feels like 1/2. So the probability of heads, given that I got a 6, is 1/2. What's the probability that I just get heads? So same scenario, but just different question. What's the probability I get heads? Well, that's 1/2. And so from a formula point of view, we say if P of A given B is equal to P of A given B, if that's equal to P of A, then those events are independent, knowing, or the second event here didn't impact what was happening to A, and that's sort of the definition of independence. So I was pretty convinced that flipping, this coin and rolling that die were independent of each other. So down here I said if probability of heads given a 6 is equal to the probability of heads, then the two events are independent of each other. If they're equal, they're independent. Not equal, not independent. So that's kind of what this part C. So going back to that problem that we were working on with annual income and age, it says, based upon your answers to part A and B, which feels pretty typical. We've calculated some two probabilities here, and sometimes in part C, we want you to tie it all into the problem. Based upon your answers to part A and B, is annual income independent of age category for those in the sample? Explain. Many times we see kids trying to sort of answer this in words. Yes, they're independent because one doesn't impact the other, or no, they're not independent because one impacts the other. It's impossible to answer part C on the AP Stats exam without some numbers and some backup. So you really can't just answer it in words. We need you to take a look at some numbers and tell us what's going on and make a decision. So I said if annual income and age were independent of each other, then the probabilities in part A and the probabilities in part B would be equal to each other, okay? P of A given B, if that's equal to P of A, then those events are independent of each other. So I went back in part A and said, well, part A was 0.43. Since 0.43 is not equal to the number that I calculated in part B, 0.364, than annual income and age category are not independent for the adults in this sample. So again, this mutually exclusive and independence are harder concepts for my students, I think. I hope I do at least a decent job teaching it to them, but really make sure that you understand those, and maybe go back and watch this again. These are very typical questions that we've asked before on previous AP exams. And again, I have absolutely no idea what will show up on this year's exam, but I'm reasonably confident, no pun intended, that there'll be some probability on one or two, maybe one or both of those free response. Again, I'm totally speculating. I have no idea. Nor does Luke. Real quick, I don't know if I'll have a chance to walk through this whole problem, but let's see if we can just start it and then I'll kind of wind down. This is from the 2010 Form B, lots of Form B, I guess, today. I don't know why that happened. An advertising agency in a large city is conducting a survey of adults to investigate whether there is an association between high level of education achievement and primary source for news. So I don't know where we're going based upon that. I see survey and I saw association, maybe chi-squared, but it's really just setting the stage. The company takes a random sample of 2,500 adults in the city. So the random's good, and that's a reasonably big sample size. I'm happy with both of those things. And there's my 2,500 again. The results are shown in the table below. And so now it's sort of maybe feeling a little bit more like probability to me. And again, I'm really trying to see if there's some relationship between the primary news, where you get your news, what source, versus your highest education level. So I think there's going to be a couple of probability questions that I'll try and wind down quickly. So if an adult is to be selected at random from this sample, what is the probability that the selected adult is a college graduate, or, so that's kind of a key word, and I don't know if I've done much with that, or obtains news from the internet. Okay. Well, what is the probability that it is a college graduate? So there's 693 college graduates. So I wrote that number down. So that felt okay to me. Or obtains news primarily from the internet. And so I kind of went across for that row there, and I had 687. But unfortunately, I'm not done here, because I guess these 245 people, I can't count them twice. So when I wrote the 693 down, I added up all of those numbers, right? When I wrote the 687 down, I guess I added up those numbers. And it feels like I added those 245 people twice. So I took all the people who were college graduates, 693. I took all of those who got their news primarily from the internet, 687. I subtracted the 245. Sometimes I call that double dipping. I've counted those twice. I've divided that by my total 2,500, and I got 0.54. And again, I always try and want to see if I can come up with a sentence here. So the probability that a selected adult is a college graduate, or, that was kind of the key word, or obtains news from the internet is 0.454. And again, I've showed my math, and I've tried to answer it in a full sentence. Part B, if an adult who is a college graduate is to be selected at random, what is the probability that the selected adult obtains news primarily from the internet? So if an adult who is a college graduate is selected at random, the probability that this adult obtains their news primarily from the internet is, well, again, it says if an adult is selected who is a college graduate, excuse me, lost my breath there for a second. There's my condition. There's 693 who are college graduates. What is the probability that the selected adult obtains the news primarily from the internet? Again, 245. So my final answer is 245 divided by 0.693, 0.354. And then this sort of feels like part C in the last problem that we did. When selecting an adult at random from the sample of 2,500 adults, are the events, is a college graduate, and obtains news primarily from the internet independent. Okay, so there's that independence again, super important. There are a number of ways to show or prove independence, but I really like the P of A given B. If that's equal to P of A, then my events are independent. If that's not equal, then they're not independent. So I tried to do it in words, in maybe math symbols, I guess. The probability that you obtain your news from the internet, given that you're a college graduate, is 0.354. That's what we did in part B. What's the probability that you obtain the news from the internet? That's 0.275. Well, I guess we hadn't calculated that. So I guess we weren't going to compare just A and B here. We needed to use what we had done in B and maybe add a third number in here. So what's the probability that you obtain your news from the internet? Well, there's 687 folks who obtain their news from the internet out of a total 2,500. So that number is 0.275. I compared those and said these events, is a college graduate and obtains news from the internet, are not independent. Why? Because 0.275 is not equal to 0.354. So that was kind of a nice little problem. In part A, we had to do something a little different there. I had to subtract out that 245. I didn't want to sort of double dip. Part B felt sort of like we had done. And in part C here, I needed to compare the two probabilities to see if those events were independent, but I guess I hadn't calculated that number right there. So I had to go back and calculate that. So let's wind down real quick for the day. Back to my PowerPoint here. So hopefully you're feeling more comfortable with solving some different types of probability questions. Again, Luke's going to do, I think, binomial and geometric tomorrow. You'll be back with me Wednesday on random variables. So we're not done, and we understand that probability can be more difficult for many students. Similar to all problems in AP statistics, you should be able to write a clear, concise solution in context. Super important. And sometimes when I'm going fast, I tend to forget to do that, but I go back and read my answer again, and I want to make sure that there's some context in there. Super, super important. Here's your homework for tonight from the 1997 multiple choice. Kind of an oldie but a goodie. I really like this, so I'll let Luke tackle that tomorrow when he starts out. So again, I finish up every one of my sessions because I think it's super important from an equity point of view. We do want all students to take the AP Stats exam this year. We realize this is an interesting year, and almost all of my kids, if not all of them, are going to take the exam, and I'm really happy about that. And we're reviewing almost every day. They have a lot of work to do between now and then, and many of them are watching these videos. They see me every day, so it's not quite as fun as to see me on YouTube. The College Board knows that not all students have access to the internet or a device. College Board's working on solutions to help students get what they need to show their best work. If you need mobile tools or connectivity, or know someone who does, you can reach the College Board directly at that link below. Please talk to your teachers, talk to someone in your school. College Board will bend over backwards and really try and help you. So we want you to take the exam. We realize that this is an interesting year, and we don't want any of those issues to be the reason that you don't take this year's exam. So thanks for watching. Happy Patriots Day. I know that probably doesn't mean much if you don't live in New England, but it's a big day for us in New England. Luke will be with you tomorrow. He'll be doing binomial and geometric. I'll be back on Wednesday for random variables. And then next week is going to be really test-taking strategies and things, how to write good answers, really focusing on this year's exam. So we're going to try and finish up the mathy component this week, and then next week will be some strategies for taking the exam. So thanks. Have a great afternoon. Please be safe. Please take care of each other. Be positive. And we'll see you on Wednesday. Thanks.